Dr. Muhammad, and I am going to speak today about the dynamic analysis fundamentals for seismic design, and I'm going to talk about the response spectrum, and this video is going to cover the first part of response spectrum. Later on, I'm going to talk about the other types, or maybe the second part is going to cover the second important concepts regarding response spectrum. Okay, let's go now to the next. So this is the title. We are talking about the dynamic analysis fundamentals. Many times whenever that I am talking about the seismic design in general, we need to think about the fundamentals related to dynamic analysis, because we are not studying here in this course, we are not going to study about the dynamic analysis in detail. This is not the scope of this course and not the concern of this course, but I'm going to explain it, or I'm explaining actually this dynamic analysis concepts, the detailed ones, in a separate course for engineers and for students. But I'm only touching some basics that is related to our seismic design. So this is why we need to put this seismic design as our main target and pick out of the fundamentals of dynamic analysis the important things for us for seismic design. Okay, so this is the main issue that we need to put in our mind regarding this video. And one of these concepts which is important and detailed in dynamic analysis courses, which is response spectrum concept. It is one of the basic concepts that we need to understand. Okay. Now let's go to the next part, which is related to the equation of motion for linear elastic single degree of freedom system. Starting from now, I'm going to use SDF. This means that single degree of freedom system. Single degree of freedom system. It is something like this. I'm going to explain about it later, but anyway, this is the meaning of SDF. And I'm going to talk about the equation of motion first for this special system for linear elastic, okay, single degree freedom system. So we're talking about linear and they are elastic. Actually, there is a difference between linearity and elasticity, as you know, because maybe for some materials even that it is going to be linear if we have kind of relation. So sometimes we are dealing with a material that is going to be linear in some part, and then it's going to be nonlinear in other part, okay? But sometimes whenever that we're dealing with these materials like concrete and steel, they are definitely linear and elastic, or nonlinear and inelastic in the same time. But some materials like shape memory alloys, for example, sometimes they are nonlinear and they are elastic in the same time. So this is why we say that our system is linear and elastic, okay? Linear means that its stress or the force versus deformation relation is linear, okay? And in the same time, whenever that we remove the load, the original position is going to be maintained again. So this is the meaning of each word in our title for today. Okay, let's go to the equation of motion. One of the most important applications of the theory of structure dynamics is in analyzing the response of structures to ground shaking caused by an earthquake. We will study the earthquake response of linear single degree freedom system. As we said, linear, it is linear here, to earthquake motions. Okay, it doesn't mean that we are not going to study nonlinear later, but it is not the right in the later stage, we are going to talk about the non-linear, okay? The non-linear single degrees of freedom and non-linear or non-linearity in general. Okay, now let's go to the equation of motion. Okay, I'm going to step directly to the equation of motion, which is commonly we can get more details about it from structural dynamics course. First of all, our equation of motion, whenever that we have a single degree of freedom system, let's go to the next slide first so that I'm going to explain in detail this equation from where it came from. So if we have a mass, as you can see here, on a trolley, and this surface is frictionless. There is no friction here. And this mass is going to be connected to a wall. This wall is moving with displacement, okay, u of g, okay, which is changing with time. It is changing with time. And it is connected with this wall with spring stiffness, with stiffness variable k, or the stiffness factor k, and it is connected also with a dashpot with damping coefficient. So now we have a mass that is connected to a wall. This wall is moving, okay, with ground, or let's say with kind of UG under displacement changing with time, and we are going to designate it with the UG. Later on we're going to talk about it as the ground acceleration. And this mass is connected to this wall through two things: spring with spring stiffness K, and dashpot link, which is having a damping coefficient. Whenever we study this equation of motion, we're going to put it in this, the equation of motion of this mass in this system. We're going to find that our mass times the total displacement that it is going to go with, which is u total, okay, and it is going to be, this is u total, okay, so we are going to have the mass times u total. This term we call it the inertia term. This term is what we call it the inertia term. So we have here three different parts that is going to, or three different forces that is going to be defining the motion of this mass. The first is whenever this mass is moving in this direction, okay, there is a kind of inertia force that is going to be induced on this mass in this direction, right? Consider that you are in a train or in a bus or whatever, okay, and you are standing here, so sorry for this, here, and you are here, for example, okay, and whenever this bus is moving in this direction, you are going to find that your inertia is pushing you back in this direction. So here, this is the direction of motion, but here, this is the inertia direction. So we have m times u total, okay, plus other term, which is the term of the damping force, which is going to be expressed through this link, which is the damping force, okay. So it is going to be C. We found it that this damping force is proportional to the velocity of the system. So we found that there is a factor or a coefficient called C. We can use it in order to express this term, which is the term of the damping. And then the last term is going to be the spring, which is going to be representing the stiffness of the system, due to the columns, beams, and so on. So we represented by spring stiffness. We found that the stiffness of the system is related to the displacement of the mass, and we can put it with, or we can express it with KU. So we can rearrange this, and I'm going to put it in this equation. Remember that U total that I'm talking about, it is actually two parts, two components. UG, which is the movement of the ground or this wall here. Actually, it is the ground here for our buildings, but here for this mathematical model or mechanical model, it is the wall here to make it clearer for us. And this UG plus the relative movement, which is U, so we can say, we can put it here that U total, it is going to equal to UG, which is U due to the movement of the ground, plus U, the relative movement or displacement of the mass with regard to this wall. Okay, so this is why we put this UG plus U. Okay, so we have here, let's arrange and put this equation and separate these terms together. We're going to find, separate them from one another. Then we're going to find mu double dot, which is the relative movement. What is the relative movement here for the real ground acceleration? If we have a shear, if we have one story building with a mass, which is here, and stiffness K for the columns, and we have damping force, which is due to the material and different sources of damping in the system, then we can say that whenever there is a ground acceleration or there is a ground excitation movement, we're going to find that the ground is moving with displacement U, we call it UG, and the structure under this movement is going to deform, and this deformation from here to here, we call it the relative displacement, which I put it here in this our equation. And we have at the end the summation of UG plus U, relative U, it is U total. Okay, so we put this equation here, which is the total equation, we put it here in more clear form. So we have m times u double dot, which is the acceleration. Sorry, this is what I'm talking about, the acceleration here. Sorry for this. So it is double dot. Okay, I'm talking about double dot. This applies well also for the displacement, but here it is for the double dot. So we are saying that m u double dot, which is the relative acceleration, which is coming from this u, plus cu dot, which is, we are dealing with the velocity, relative velocity, and ku, which is dealing with the displacement, relative displacement. So we are talking about u dot and u double dot. The first term is related or expressing the inertia force. The second term is related or expressing the damping force, and the third term is dealing with the elastic force. Okay, so here, as we mentioned here, there was a term for u double dot g. Then we put it in the right hand side, so we put it here with negative sign, m u double dot g dot t. Okay, m u double dot g of t, and this is what we call it the ground excitation, the ground excitation term, the ground excitation term. Okay, so I hope that for our case, sorry for this. So here, let's go back again and see. Our equation now is going to be mu double dot plus, which is the inertia force, this is the damping force, plus the elastic force, equals to minus m u double dot g of t, because this u g of t, it is changing with time. Okay, this is the equation of motion governing the relative displacement or deformation, which is, we are talking, this is the relative deformation or the deformation of the linearly. Again, we're talking about linearly and elastic, and we understood now what is the meaning of this, structures subjected to ground acceleration, which is u double dot, okay, u double dot of g, or u double dot g of t. Okay, this is the ground acceleration. So this is the equation of motion for the ground excitation for any single degree of freedom system. This is for any single degree of freedom system. Okay, so now as we have understood now this equation, we can go to the next step. One thing that is important for us to highlight, that is why we are highly in putting u double dot g here. U double dot g can be easily recorded in practice. U double dot, which is the acceleration of the ground motion. Whenever that we have a ground motion, it might happen that this ground motion is can be like expressed by displacement u or velocity u dot or acceleration u double dot. Commonly, the devices that is being used for recording earthquakes, it is easier for it to use u double dot than using any other component of the wave to be recorded. So u double dot is easier to be recorded. This is why you're going to find that u double dot g is our main representative of the ground motion. Okay, our main representative of the ground motion. Okay, so now let's go to next part. Now we have our equation and we understood it. Okay, as I said, every term, if we go back here, the first term is expressing a type of force different than the other. So we have here the first term is inertia, the second term it is damping force, the third term it is the elastic force. The elastic force is the most important for us because knowing Ku, this means that we are going to obtain we are going to obtain all the forces and beams and columns. So this is why it is important for us to know Ku. Even that Cu dot is important and Mu dot is important, but at the end we are going to rely on Ku or the elastic forces in order to obtain the stresses and forces and beams and columns. Okay, so that's the equation of motion. Let's go further in this equation of motion and try to understand it in more details. So this is the equation of motion, as we said, mu double dot plus c u dot plus k u equals to minus mu double dot g. If we're going to divide this equation by m, so divide this equation by m, it is going to give us u double dot here, and this c, actually it equals to, c equals to 2 zeta omega n times m. So this is theta, okay, this is here the value of the c. So it equals to 2 times the damping ratio times omega n times m. Okay, so if we are going to, this is from the dynamic course, you can get it from the dynamic course. Okay, this is the damping coefficient, and it has a relation with the damping ratio and the natural frequency of the system and the mass. So based on this, if we divide this term with m, then we're going to end up with 2 zeta or 2 damping ratio times omega n, which is already, I put it here, and m is going to be cancelled out. And we have u dot here, plus omega squared n, because we have k here, and remember that omega squared equals to k over m. This is one of the fundamental equations in and fundamentals of dynamics. So you can find it easy also in dynamic course. Based on this, we're going to find here omega squared n equals to minus u double dot g, which is mu double dot, m will cancel, and then we're going to end up with u double dot g and the minus sign. So what is the point here? The point that we want to highlight is, look at this equation deeply. You're going to find that u double dot, u dot, and u, which are the acceleration of the mass, the velocity of the mass, and the displacement of the mass, they are function of what? The acceleration of the ground acceleration, the acceleration of the ground excitation. Okay, so this is the main thing that we are talking about, that these three items or these three quantities, they are related to u double dot g, and in the same time that they are going to be influenced by zeta, which is the damping ratio, and omega n here and here. So this means that, which is the natural frequency. So we can put this note. It is clear that for a given u double dot g of t, what is the meaning of this? For any ground excitation, that's the meaning. The deformation response, which is u of t, of the system depends only on the natural frequency, omega n, which is in terms, it is related to t, because as you know that we have omega or Tn equals to 2 pi over omega, or the opposite. So Tn, the natural period of the structure or the system, equals to 2 pi over omega. Okay, so we can say that the term U, or this system deformation, is going to rely on omega n, or the natural period of the system, and its damping ratio. So this is the second thing here, the damping ratio, and Tn, the natural period and the damping ratio. So writing it formally, we can say that U is function of small t, which is the variation of time of this ground excitation here in the right hand side, the acceleration of the ground excitation, and Tn, which is the natural period of the system and the damping ratio of the system. Okay, thus any two systems having the same values of Tn and zeta, damping ratio, will have the same deformation response U of t, even though one system may be more massive than the other or maybe stiffer than the other. What is the meaning of this? Here we are trying to say that take care that what really U is relying on is the t, the time of the ground excitation, the point of time and the ground excitation, Tn, which is the natural period, and the damping ratio as well. Right? But there is no direct relation between U and the mass and the stiffness. But actually this is not clear. We are dealing with the ratio, which is K over M. This is our main concern here. We are not dealing with K only or M only, but U is relying, or it is linked to, or proportional to K over M in a certain way. Actually, if you looked at this equation, we have Tn equals to 2 pi over omega, and we know from here that omega equals to, omega squared equals to K over M. So here we can say that Tn equals to 2 pi over the square root of K over M, stiffness over the mass. This means that if the system, okay, if the system, if the system has like stiffness like 100 over mass, which is 50, it equals to another system that is having a stiffness of only 10 over mass equals to 5. So even that the mass here is very huge and the mass here is very small, but actually they are going to have the same response, because the stiffness here also is very huge, but here it's very small. So we're talking about the ratio here. This is why we said that Tn is the most important thing. Tn is the most important thing. It has a relation, Tn is having a relation with the reciprocal of the radical of the ratio K over M, as we can put it here. Okay, I hope that you could understand this point. Okay, now let's go to the next part. We can say that ground acceleration, okay, we can say that ground acceleration during earthquakes varies irregularly, okay, to such an extent that analytical solutions of the equation of motion must be ruled out. Okay, the question now is how we can solve this equation. We have some equation, we have some ways for the solution, like Duhamel's integral, okay. In dynamic analysis, we explain this system, or how we can solve this, or analytically, okay, analytically how we can solve this differential equation. It's easy for us to solve it. But the problem is the type, the earthquake is what? Yes, exactly. It varies with time. So we need to solve this equation at every point of time of the earthquake. So if we have an earthquake with different values, okay, this is the spreading time t, and this is the acceleration of the earthquake. So at every point we need to calculate over and over and over again, because really we do not know what is the input. The input every time is going to be changed. U double dot, okay, sorry, U double dot of G, it is going to be changed every time. Every time it is going to be different than others. So we do not know what is the response of the structure. Okay, so this is why analytical modeling, analytical solution is not going to work for us. Okay, we need to think about other way for our solution, or for the solution of this equation. Okay. One of the ways for the solution, one of the ways of this solution that we are talking about here is numerical methods. So therefore, this is what we say, that numerical methods are necessary to determine the structural response. So we use like numerical methods, okay? Numerical methods. This is the best way for the solution. Okay, now let's go to the next. Let's go to the response quantities that we are going to deal with, okay, whenever that we are talking about the single degree freedom system. Okay, what are the most important ones? Okay. Of greatest interest in structural engineering is the deformation of the system. Yes, deformation is very important for us. Or displacement, which is U of t, of the mass relative to the moving ground. That's very important. We are talking about U of t. As I mentioned before, that we have U of g of the ground. This is the ground excitation displacement. And we have ut, which is the total movement or displacement of the mass. But we have u, which is the difference between u total and ug. So we have u. This one is with great importance for us, because from this one we can tell what are the internal forces going to be developed. Because if we have like a ground excitation that is going to make our system, if we have a system like this, and then there is a ground excitation and the system moves like this, it moves exactly as a rigid body motion, then there is nothing happened for the system. There is nothing happened for the system. It is the same, only moved, okay, with this u total, but there is no kind of deformation for the system itself, right? So we need to understand what is the deformation happened for the structure, for example, here. This kind of relative movement, that is, I'm talking about u, this would make the internal forces, okay, to be induced. These are the bending moments and shears in the beams and columns of the one-story frame that is going to be here, okay? This is the bending moments that is going to be developed. All bending moments and shears that is going to be developed in our system, okay, are going to be due to u. Not due to u total, it is related to u, not u total and not to ug, okay? So this is the bending moments here and shear and so on in columns and beams, and it is going to be the spring force in our spring system here, the spring force in our system here, okay? This is the spring force here. So the internal forces in the one-story shear building here, or one-story building here, is going to equal to the spring stiffness that is going to be developed in this mathematical model, okay? Okay, now, sometimes it is important to know about u total, okay? There is u total that I was talking about here. So this one, sometimes it is important, okay? So if we're going to talk about u, this means that we're talking about internal forces in beams and columns. But if we're going to talk about u total, then it might be important for other cases, which is something like this. We call it in the bounding, okay? Pounding of different buildings. As you can see here, this is one picture, two images actually, of pounding damage to the in Mexico City. This was in Mexico City due to Mexico earthquake in 1957. As you can see here, look here, there was kind of pounding between the two. There is colliding between the two buildings, this short building and the tall building. You can see it here also in this part. Why this happens? Because they didn't consider UT, the total displacement of this building and the total displacement of this building due to under the earthquake. Okay, so the mass would be useful in providing this U total is going to be important and useful in providing enough separation between adjacent buildings to prevent their pounding against each other during an earthquake. So pounding is the cause of damage to several buildings during almost every earthquake. So in most earthquakes, you're going to find that pounding phenomenon is going to take place in one place or another. So this is the importance of U total. Okay. So now again, U total is important for something related like pounding, for example. Okay, but U, the relative displacement, is important if we're going to talk about the bending moment and shear forces in beams and columns, which means that it is important in internal forces. Okay, it is important in internal forces for us. This is important in pounding. U total important in pounding. U, or the relative movement, is important for obtaining the internal forces, which is the bending moments and shearing force for our structure elements. Okay, now let's go to the next part. Okay, now similarly, the total acceleration of the mass would be needed. Okay, total acceleration of the mass. So now we were talking about when it is important to think about U relative and U total. We mentioned about what is the importance of this one and what is the importance of this one. Okay. Similarly, the total acceleration of mass would be needed if the structure is supporting sensitive equipment. So we are dealing with the total acceleration, which is of the mass, which is this one. Total acceleration of the mass. Because if we have some equipments, okay, on buildings, for example, this is an important like equipment. And what we are interested in here, it is not how much displacement the structure is going to go, because it might be going as a rigid body motion. But the problem is, what is the acceleration that is going to take place between the two? So we're dealing with U double dot T here, okay? U double dot T. So the total acceleration of the mass would be needed if the structure is supporting sensitive equipment. That's important for us. This is the case. Sensitive equipment. And motion imparted to the equipment is to be determined. Okay, in many cases, we are interested in the total acceleration. Take care here. We are talking about total acceleration. We didn't mention about the relative acceleration. Okay, it's not our concern here. Our concern is the total. Okay, because this is going to make some, or this is critical for the sensitive equipments. Okay. The numerical solution can be implemented to provide results for relative and total quantities. In general, all of the quantities, whether that is it is relative for displacement, velocity, and acceleration, whether relative or total, we can use what? Numerical solution for obtaining this. So numerical solution is our main target, but it's time consuming. It's time consuming. This is why we are going to find that response spectrum is going to be our alternative. Now we understood what is the problem, and we need to go through what is the solution, or what is the alternative for the numerical solution. Okay. Okay. I'm going to talk about the response history first before going and indulging into the response spectrum method. We need to talk about the response history. Okay, we want to understand what is the meaning of this. Okay, so first of all, response history is the deformation response of a single degree of freedom system. Okay, this is the deformation. If we're going to talk about that, the vertical axis, okay, is going to give us the deformation, for example. Horizontal axis is going to give us the progression of time. Okay, this is the time over t. So if we are going to use one earthquake, let's assume that we are talking about El Centro earthquake. This is the earthquake that we are going to use here. Okay, El Centro earthquake. El Centro earthquake. In El Centro earthquake, you can, if we are going to assume that we have different single degrees of freedom system, okay, let's assume that we have different degrees or some single degree freedom system, and it has different characteristics. Let's assume that it's Tn, which is the natural period of this system. Let's assume that one time it is 0.5, another time it is 1 second, and a third time it is 2 seconds. And let's assume that our damping ratio is going to be constant, 0.02, 0.02, 0.02. Okay. Then we're going to draw the response of the displacement u. Okay, we're talking about u now, of this single degree of freedom system. Okay, this is u at different times, as you can see here. So we have 3 different models, 3 different degrees of freedom, and we have 3 different degrees of freedom, and we that 3 different single degree freedom system. As you can see, every one, it has its own natural period, Tn here, 0.5, 1, and 2, and the damping ratio is going to be the same. Okay. Then from the UG double dot, which already we have explained before, we can plot this response spectrum. Remember that? I'm going to recall our main equation. This is our main equation. So we have, this is U double dot. Let's go to the previous one. Yes, this equation. So now we have damping ratio and omega n. They are our main parameters. I said that we change Tn here because it is related. Tn is going to be changed 0.5, 1, and 2. And we have the damping ratio. We assumed it to be 0.02. And U double dot G is going to be used based on El Centro. So already we have the acceleration of El Centro, and it is known for us. So now we can obtain this U dot and U double dot, but we are interested now in U. Let's see what we are going to have. So this is U now. We're talking about U here. Okay? So we found that, look to the response here. Look to the responses here. Okay? The response is going to be, as you can see here, it is a little bit small here, but the maximum one is 2.67. And for the case of Tn equal to 1, we found that the response in comparison with the previous one with the Tn equal to 0.5, we can find until that it's a little bit larger, right? Especially in the first portion of it. And we recorded the maximum value to be 5.97. And for the case of Tn equal to 2 seconds, we found that the response is considerably higher than the 2 cases, and we found that the maximum is going to be 7.47. This means that with the increase of our natural period, the response or the deformation or the lateral displacement is increasing every time, as you can see. Right? This is an important observation. This is an important observation. Okay. So this is the this is the effect of what? Of the natural period. What is the effect of and now we have the damping ratio is constant, right? Okay, now let's go to the opposite. Let's flip this. Let's assume that we have the single degree freedom system, only one system, okay, with 2 seconds period, and we change only the damping ratio from 0 to 0.02 to 0.05. So we have like 3 different values for the damping ratio. However, that the natural period, it is the same, 2 seconds, 2 seconds, and 2 seconds. Let's see this. You're going to find that the deformation in the first case is 9.9, then the maximum one, and then when we go to the case of 0.02 damping, we found that the deformation is 7.47, and when we go to the last case 0.05, we're going to find that it is 5.37 inch. Okay, this means what? It is decreasing every time the deformation is decreasing. So with the increase of the damping ratio, there is decrease in the displacement. Okay, that's very important issue. So increasing the natural period is increasing the displacement or the response, but increasing the damping ratio would decrease the response of the structure. Okay, that's one thing that is important for us, and this cannot be understood unless that we know the time history of our system. Okay, now once the deformation response history U of t has been evaluated by dynamic analysis, this is this one, I mean that any one of them, so this is the response, okay, this is the displacement response, okay, by dynamic analysis of this. The internal forces can be determined. So now how we can obtain the internal forces? How we can obtain the internal forces? Okay, by static analysis of the structure at each time instant. So we are going to say that f of s equals to k times u. Now we know u, right? U, it is at each instant of time. We know it already from the previous slide. Okay, we can obtain u at any point. At any point we can obtain our u. It is already this graph. It is already obtained, okay, for us using the solution of the main equation of motion. Okay, now after knowing u of t, we can multiply it by k, which is the stiffness of the system, and then we are going to obtain f of s. So this is the elastic forces that is going to be developed at each time instant. Okay, so it is variable. It is variable. And this f of s is going to be as if it is the lateral force applied at this level of the structure. Then, knowing this f of s, we can obtain the moment, okay, and the base shear that is needed for developing the foundation or designing the foundation, and we can know the overturning moment, right? F of s or fs of t times h is going to give us the overturning moment. So this concept is very famous, and a very famous concept actually in earthquake engineering. The concept of equivalent static force, which is f of s, as shown, is used because it can be related to the earthquake forces specified in building codes. Building codes, they are interested in this. They say that they are going to give a kind of force that is applied laterally to the structure, and f of s, based on this system, based on our understanding, is most suitable for them. Okay, so k times u of t. Remember that u of t, we obtained it from the equation of motion, by the solution of the equation of motion. K, it can be defined easily. K is the lateral stiffness of the frame. If we know our columns here, then our K can be obtained easily. Okay, so this is the meaning of our f of s. Okay, this is how we can obtain the internal forces after that. This f of s, we can use static analysis, and we can get the lateral forces, the internal forces in beams and columns and joints. Okay, now look to this f of s. As we said, f of s equals to k times u of t. Okay, as I said, remember well that we have omega squared equals to k over m, right? So k here, we can put it as m times omega squared n times u of t. But this is f of s, right? which means force. Force, if you look, force means what? Means mass times acceleration. So this part is going to be, must be acceleration, because this is force. If we are going to apply Newton's law, so the force equals to mass times the acceleration. So omega squared natural circular frequency squared times u of t must equal to the acceleration. We call it the pseudo-acceleration here. So a of t equals to omega squared times u of t. Okay, as simple as that. So our f of s, we can assume that the acceleration of the single degree, we're talking about single degree of freedom system, remember will, right? So if we know u of t of this system at any point of time, then we can obtain u double dot of t. Very easy, right? How we can obtain it? From here. We're going to multiply our u of t by omega squared n. That's it. Then we are going to obtain our u double dot of t. Okay? The acceleration is going to be important for us, as we said, for if we are going to deal with specific, or if we are interested in calculation of the acceleration of the system. Okay? So now, if we have the response spectrum, or if we have the original deformation response u, which is already obtained from the solution of the equation of motion. This is already, we have mentioned about it a few slides before. Okay, then we are going to multiply this graph by omega squared n. That's it, which is equal to 2 pi over Tn to the power 2. Okay, 2 pi over 2 Tn to the power 2. This is omega squared. Okay, this is omega squared. Then if we multiply the u, the deformation u, by omega squared n, we are going to obtain what? The acceleration. Okay, we call it the pseudo-acceleration. The acceleration of the system. That easy. We can get it in this way. It is very easy for us to obtain the acceleration. So now, if we say this is 2.67 multiplied by omega n squared, omega equals to 2 pi over Tn to the power 2. We know Tn here. Multiply it omega squared n by this value, or by each value here along this graph. You can obtain the maximum acceleration, and you can obtain the acceleration at each time instant on the graph. So this is what we call it, the pseudo-acceleration. We can repeat it for any other types or for any other systems, as you can see, and we can obtain the acceleration or the acceleration graph, the pseudo-acceleration graph. Okay, this is regarding this issue, or this is regarding the response history and the relation between the deformation of the system and the acceleration of the system, how we can obtain it. Okay, this is a very important concept in response spectrum that is going to be used later on when we are developing the response spectrum curve. Okay, now that's very easy for us. After that, for the one-story frame, the internal forces, okay, means that the shear and moments in the columns and beams or stresses at any location can be determined at selected instant of time, at any instant of time. That's the meaning of at selected instant, by static analysis. So now we can use our very simple static analysis of the structure subjected to the equivalent static force, lateral force F of S, at any time at the same time instant. So here now we have F of S, which is already obtained from this equation that we have mentioned 2 slides before, and then we can obtain the base shear and the moment at any time. Okay, V base equal to F of S, and M base equal to H times F of S. That's it. And this is for the V base and M base. If we're going to use the acceleration instead of the deformation, then V base is going to equal to M times A of t, which is already obtained in the previous slide. The mass times A of t that is obtained before, then we can obtain the V base. Okay, and this M base is going to be H times V base that is obtained here. Okay, so this is how we are going to deal with. Why we are telling this story? Because we want this equation at the end. This equation is important, that the acceleration here is needed, because we are going to multiply the mass times the acceleration, or the pseudo-acceleration, then we are done. We will have the base shear, and we can get the internal forces in our structure. Okay, so that's the first important part, or this is an important part, that is obtaining A of t would make it our life easier to obtain the base shear. Okay, now I'm going to talk about the response spectrum. Okay, I'm going actually to stop here this video, and I'm going to resume the next part of the second part of the response spectrum in the next video. Thank you.